Hello, it's Stat 134, Lecture 2. Last time we covered the addition rule and the inclusion-exclusion rule, which are both OR rules. So the addition rule says that for mutually exclusive sets, the probability of A or B is just the sum of the unconditional probabilities. The inclusion-exclusion rule allows for the possibility that A and B have an intersection, in which case we need to subtract off the probability of having that intersection, because that intersection is double counted. It's included both in the probability of A and in the probability of B. Today we're going to do section 1.3, 1.4, and 1.5. First we'll start off with just some easy facts about sets, in that the order that you take unions does not matter. And so the expression on the left here with the union of three events can be generalized to a union of m plus 1 events. So you can write a union of m plus 1 events by first taking the union of m of the events and then taking the union of the last one. Furthermore, the union and intersection, which I write as multiplication here, distribute. So the expression on the left shows how when we have three events, that if I take the union of A1 and A2 and I intersect that with A3, that's just the same as taking A1 intersect A3 union A2 intersect A3. And how this would generalize is shown on the right. So we begin with a proof by induction. So a proof by induction has two main steps. You show a base case, and you show that if some statement is true for n, then it's also true for n plus 1. And the conclusion is that the statement is true for all n. Okay, so here is an example, one that's might be helpful for number 12 on your homework. So we have n plus 1 events, and we want to show that the union, the probability of this union has the expression shown here. So to prove this by induction, we show the base case, which is when n is 1, and that is actually just the inclusion-exclusion rule, so that is true. Now we're going to assume that this is true for a union of n events, and we're going to show it's true for a union of n plus 1 events. So the idea here is that the probability of n plus 1 events, we can write that as the probability of the union of n events union and n one more, the last event. And so we've just basically written the union in this way, and we saw above that we can do this. So now we're just going to realize that all that we're writing here is we're looking at the probability of the union of two different events. One, however, is itself a union. And so by the inclusion-exclusion rule, this is the probability of that union of AIs plus the probability of AN plus 1. And then you have to subtract the probability of the intersection. And the probability of the intersection is, as shown in orange here, is the probability of the union of the AI intersect the last term, AN plus 1. But this is just the same as the probability of the union of these AI intersection AN plus 1. And that's exactly what we needed to prove. So by the principle of mathematical induction, we've shown the claim is true for all n. So now a named distribution that you should be aware of is called the uniform distribution. And the uniform distribution essentially means that, well, so in particular, this is the uniform distribution on a finite set. And it just means that you're randomly choosing any one of the elements in your finite set randomly, so like out of a hat. So the probability of you getting any one of those n elements, x1 to xn, is 1 over n. And so that's the distribution. It's called the uniform distribution. So for example, suppose a word is randomly picked from this sentence. What is the distribution of the length of the word picked? So we have shown in red here the length of all these sentences. So this would be uniform on this set of numbers, and notice that the numbers can repeat. We then did a concept test. A deck of cards is shuffled. What's the chance that the top card is the king of spades or the bottom is the king of spades? So it's impossible for the top card to be a king of spades and at the same time to be the bottom card to be a king of spades. So those two events are mutually exclusive. So this is an OR, so we're going to use the addition rule. Now the addition rule should be the probabilities of each of these events occurring, which is 1 out of 52. So that is none of the above. I will mention that it's not possible to make a scenario like above that would give you B, since these are unconditional probabilities. So it should always be 1 out of 52. We're not conditioning on anything that happens before or after. Now if I change the wording so that now the bottom card is the queen of spades, now we're going to use the inclusion-exclusion formula. And that's C. The last term here is the intersection. It's the probability that the top card is the king of spades and the bottom card is the queen of spades. This follows from the multiplication rule that we're going to talk about now. So we're on to section 1.4, conditional probability and independence. So conditional probability is the probability of A given B. So we write this vertical line and we say given. So what it does is it restricts the outcome space to B. So from omega to B, because we know that B is true. So now the probability that we have A given B would be the area of A that's in B divided by the area of B. So that's the probability of AB over probability of B. And if you just cross multiply, we get what's called the multiplication rule. And this is an AND rule. So it's the probability that you have A and B, the intersection of A and B. So we say that A and B are independent if the probability that you have A given B is just the probability of having A. So the fact that it's given B does not affect anything. This is equivalent to saying that the probability of A and B is equal to the probability of A times the probability of B, because if you look at the multiplication rule, the probability of A given B is the probability of A when A and B are independent. So, so here in this last example, with the queen of spade and the king of spade, that's why we get 1 over 52 times 1 over 51, because the conditional probability is 1 out of 51. We're conditioning on what the first card is. So on to section 1.5. A factory produces 2 models of cell phones. So given that you have model 1, the probability that you have model 1 is 0.3. The probability that the phone is good, given that it's phone 1, model 1, is 0.8. Probability that it's good, given that it's model 2, is 0.9. You can make a tree of this and figure out, for example, what all of these probabilities are. So the probability that you have model 1 and it's good, so that would be the top branch. So 0.3 times 0.8. Probability that you're good would be the sum of the 2 yellow branches, because to be good, you can be good in model 1 and you can be good with model 2. And those are mutually exclusive events, so we would add them. And you can find the probability that you're 1 given that you're good using Bayes' rule. And we know each of the components for Bayes' rule computed above. And I should note that Bayes' rule can be written in a more complicated way if you expand what you mean by the probability of 1 and good, and probability of good, just as we've done above. So that's the end of the show for today. Have a great weekend.